Good morning, dear students and Ma'am Sharada. Today we're gonna discuss about the colligative properties of a solution. The objective of this lesson is to describe the effect of concentration on the colligative properties of a solution. And second is to differentiate the non-electrolyte solutions and electrolyte solutions. Third is to calculate the boiling point elevation and freezing point depression in the concentration of solute in a solution. Let's now proceed to Ms. Solomon to discuss the colligative properties of a solution.
Thank you, Ms. Artida. So for today's video, I'm going to discuss the vapor pressure lowering and the boiling point elevation. But first, let us know the meaning of colligative properties. Colligative properties are properties that depend on the number of solute particles, not their chemical identity. This means that similar amounts of completely different solutes can alter these physical properties in similar quantities. Hence, the colligative properties depend on the ratio of the solute amount and solvent amount. Colligative properties include vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Let's move on to the vapor pressure lowering. The vapor pressure of a solution containing a non-volatile, non-electrolyte is always lower than the vapor pressure of the pure solvent. Vapor pressure lowering is a property associated with ideal solution. Let's take a look at an example here. Here we have a container. These two containers are at the same temperature. This one contains pure solvent and the other one contains a solution with a non-volatile solute. Let's pretend that the solvent here is water, and here we have a solution of sugar water. So sugars are non-volatile solute. These two containers, as I said, has the same temperature and they were completely evacuated when the liquid was put in. So the only gas present is the vapor of the solvent. So we have water vapor here and we have water liquid here and we have water vapor here and we have the water as a solvent in the solution here. If you look at the pressure gauge up here, you can see that the pressure, which is the vapor pressure of the water, is about 3, and the vapor pressure here is about 2. And so what we see from the evidence is that the vapor pressure of the solution is lower than the vapor pressure of the pure solvent. The question is, why? We have to remember that the vapor pressure is an equilibrium condition, which means that the rate of the particles in the liquid phase going into the gas phase is equal to the rate of the particles in the gas phase going to the liquid phase. In both cases, in the case of a solvent and a case of the solution. Now, the fact that the vapor pressure is lower here tells us that there are fewer gas moles present at the equilibrium condition for the solution. So why is the free energy lower? Let's take a look at some data. Here are some examples of just pure solvent and here a solution of a non-volatile solute. You can assume this is water and this is sugar water because sugar would be an example of non-volatile solute. When you put these two, the liquid versus the solution, in containers of the same temperature and measure the vapor pressure, you see that the vapor pressure here for the pure solvent is about 3, whereas the solution is about 2. So it's lower. Experiment after experiment shows the same results. The vapor pressure is lower. Why is that? Well, the vapor pressure is lower because at the surface. It's a surface phenomenon. There are different molecules taking up space at the surface and therefore there's fewer molecules that are getting into the gas phase. Another way to think about it is the fact that the free energy is equal at the equilibrium condition, and so the free energy of the solution is lower, therefore the free energy of the gas phase would be lower as well. Nevertheless, it's a phenomenon that occurs repeatedly. Let's take a look at the phase diagram of solutions. Here we have a phase diagram line for a pure solvent versus the diagram lines for solution. This particular line here is the vapor pressure line, and you can see at any given point, here is the temperature, here's the vapor pressure of the solution, here's the vapor pressure of the pure solvent. The vapor pressure of the solution is lower all along the lines. One consequence of this is that boiling temperature is actually higher for the solution. The solution boils at a higher temperature because you have to get into a higher temperature to get it up to that 1 atmosphere pressure, to get the vapor pressure up. So we see this all along the line at any point in time. The solution vapor pressure is lower than the pure solvent. Raoult studied this phenomenon over and over again and came up with a law. Raoult's law states that the vapor pressure of the solvent above the solution is proportional to the mole fraction of the solvent present. And here's the equation of Raoult's law. Rolle's law can be extended into the notion of colligative property, which is the property that depends on the amount of solute and not the type of solute, as long as it, in this case, is a non-volatile solute. The vapor pressure lowering is proportional to the mole fraction of the solute present. And here's the equation. Next is boiling point elevation. The normal boiling point of a liquid is defined as the temperature at which the vapor pressure of the liquid is equal to the standard pressure, or 180 m. If we can change the external pressure from 180 m lower or higher, the boiling point changes as well. The boiling point is then simply the temperature at which the vapor pressure of solvent equals the pressure of the surroundings. The first thing you need to know is that the solution or liquid boils when a solution vapor pressure equals the atmospheric pressure. We know a vapor pressure is a pressure that exists at the surface of a liquid, and you can see this in this illustration, that a container here is filled with a liquid and the surface is represented by this blue line up here, and these blue molecules are supposed to represent individual liquid molecules making up the entire liquid. And at the surface, some of these liquid molecules are turning into vapor. They're evaporating. Others are condensing back into liquid, while others are evaporating and condensing over and over. And this is happening many times per second, and it's generating a pressure at the surface of this liquid called a vapor pressure. The atmospheric pressure is the surrounding pressure of the entire room that this container is sitting in. So the atmospheric pressure is the pressure of the entire atmosphere in which this container is placed, while the vapor pressure is the pressure right at the surface of the liquid. And what we have to understand is that when two pressures become equal, that is when this liquid will boil. So we know that there's a way to actually lower vapor pressure through Rolle's law. And Rolle's law says that if we were to dissolve a non-volatile solute in this liquid represented by these red dots, it essentially crowds out the surface of the liquid, thus making it harder for the blue molecules to evaporate and condense and generate the same vapor pressure. So it's actually harder to boil the container of solution with the red dots than it is to boil solution in the other container, and that is because the solution has lower vapor pressure, and we have to get the vapor pressure up to the surrounding atmospheric pressure to begin boiling. So this brings up some interesting questions. You may have heard that it's actually easier to boil water at the top of the mountain. Why is that? Well, at the top of the mountain, atmospheric pressure is actually very low. That means it's easier for vapor pressure to reach atmospheric pressure and begin boiling. Also, why do people add salt to water before boiling it? Well, think about this example here in the illustration. The salt is like the red dots. If we add a non-volatile solute such as table salt to water before boiling it, it lowers the vapor pressure solution, thus we have to get the solution at a very high temperature, higher than normal, to boil. It actually means that your water is going to boil at a higher temperature, thus you can cook your food faster. When a solute is dissolved in a solvent, the boiling point of the solution is raised according to the equation. Delta Tb is equals to Kb times m, where delta Tb is the change in temperature, m is the molality, which is the moles of solute per kilograms of solvent. Kb is the molal boiling point constant. Next is Ms. Hanoras to discuss the freezing point depression and osmotic pressure.
Thank you, Ms. Solomon. Next is the freezing point depression. The word depression means something low or something down. The normal freezing point of a liquid is the temperature at which a liquid becomes a solid at 180 m. Freezing point is the temperature at which solid and liquid phases coexist in equilibrium. A solution always freezes at a lower temperature than the pure solvent. The question is, why does the freezing point depression occur? At the freezing point of a solvent, there exists an equilibrium between the liquid state and the solid state of the solvent. This implies that the vapor pressures of both the liquid and the solid phase are equal. Upon the addition of a solute which is non-volatile, the vapor pressure of the solution is found to be lower than the vapor pressure of the pure solvent. This causes the solid and the solution to reach the equilibrium at lower temperatures. So what happens at the freezing point? Freezing point is when the liquid becomes a solid. Increased pressure as with melting point typically increases the freezing point. Let's go to the equation of freezing point depression. The freezing point depression is proportional to the molality of the solution. The equation is freezing point depression equals Kf times m, where the first symbol refers to the freezing point depression. Kf is the molar freezing point depression constant for the solvent, and m is the molality of the solution. Next is the osmotic pressure. Osmosis is the movement of solvent particles from a region of higher to a region of lower concentration through a semi-permeable membrane. Solvent will always flow from a dilute solution to a more concentrated one. Osmotic pressure is the pressure that must be applied to prevent the net flow of solvent. Here is the formula or equation for osmotic pressure, where the pi symbol refers to osmotic pressure, m is for molarity, r is the gas constant which is equal to 0.0821 atmospheric pressure per liters over mole per molal, and T is the Kelvin temperature. Next is Ms. Marchand to discuss the electrolyte solutions.
Thank you, Ms. Hanoras. So let's now talk about the differences between electrolyte and non-electrolyte solutions. We have here an overview on how these two solutions differ from each other. First, the electrolyte solutions. Electrolyte is a solution that generally contains ions, atoms, or molecules that have lost or gained electrons and is electrically conductive, while non-electrolyte is a solute that does not dissociate or separate into ions during the dissolving process. To broaden your knowledge about these two solutions, let me explain what electrolyte is, while Ms. Del Ballesteros will explain what non-electrolyte later on. Electrolyte solutions. Electrolyte are substances that have a natural positive or negative electrical charge when dissolved in water. Like what I've said earlier, electrolyte is electrically conductive. To simplify, electrolyte are salts or molecules that ionize completely in a solution. As a result, electrolyte solutions readily conduct electricity. This means that this type of solutions has ability to carry a current. Some examples of these are sodium, chloride, potassium, magnesium, and calcium. These solutions are normally formed when a salt is placed into a solvent, such as water. This is because when a salt dissolves, its dissociated ions can move freely in a solution, allowing a charge to flow. That's why it is an electrically conductive. Let's now call for Ms. Del Ballesteros to explain briefly what non-electrolyte is. Mr. Ballesteros?
Thank you, Marchan. So, unlike electrolytes that conduct electricity, non-electrolytes are the exact opposite. Since when a non-electrolyte is dissolved in a solvent, they do not create conductive solutions or any other conductive species. The most common example is sugar, like glucose and sucrose, because when sugar is dissolved in water, instead of dissociating into ions, it forms into molecules that are not conductive at all. So, let's just put it like this. So, in order to conduct electricity, a substance should have really mobile charge species, just like the metal wires of our cable chargers. And in a solution, these wires are the ions. And non-electrolytes don't have that. They don't ionize, because the higher the ions, the greater the conductivity. So therefore, non-electrolytes cannot conduct electricity. So What do you guys think are the differences between colligative properties of electrolytes and non-electrolytes? So we can see here in the table that electrolytes contribute more solute to the solution. That results in a change in a colligative properties. And because non-electrolytes do not dissociate, they only add a small amount of solute to the solution. So because electrolytes provide more solutes, they have a much higher effect or impact on colligative properties than non-electrolytes. So those are the differences between electrolytes and non-electrolytes. So here is Angela Arquita that will show you the calculation of boiling point elevation and freezing point depression.
Thank you, Mr. Ballesteros.
Now let's try to calculate the boiling point elevation. What is boiling point elevation? Boiling point elevation, as mentioned earlier, is that when you add solute particle to a solution, the boiling point will go up or increase. And for example, when you add salt to a water, the boiling point elevation will increase. So now let's try to solve this problem. When 20 grams of sodium hydroxide was dissolved in 200 grams of water, calculate the boiling point of elevation. So, what is the formula of the boiling point elevation? The formula of boiling point elevation is delta T is equal Kb. Kb is the boiling point molar, and M is multiplied by M, and M is for the molarity. So we have here are given 200 grams of water, 20 grams of sodium hydroxide, and molar boiling point of 0.51. And the formula that we're going to use is we're going to derive it from the T solution minus the H2O equals Kb times M. So we're going to move this THO2 to the right. So we have T solution equals Kbm plus T H2O. In this problem, we are missing the molarity. So first, let's input and find the molarity. We have the given here 20 grams of sodium hydroxide over 1 times 1 mole of sodium hydroxide. Let's first find the molar mass of the sodium hydroxide. The atomic weight of sodium is 23, oxygen is 16, hydrogen is 1. Let's just add this all and it is equal to 40. So in every 1 mole of sodium hydroxide, it has a mass of 40 grams. And we're gonna cancel the unit of grams, cancel. And first we're gonna need to convert our solvent 200 grams of water into kilograms. So what we need to do is 200 grams divided by 1000 is equal to 0.2 kilograms, and we're gonna put it here. So multiply by 1 over 0.2. So 20 grams of sodium hydroxide over 1, so 20 divided by 40 is 0.5, and 0.5 divided by 0.2 is equal to 2.5 molar. So the molarity of the solution is 2.5 molar. So we have the missing mole of the solution, and let's input the given numbers to the formula. So here is the boiling point of water. The boiling point of water is 100 degrees per Celsius plus the molar of the boiling point is 0.51 degrees Celsius per molarity times the mole of the solution is 2.5. So equal so we have 0.51 times 2.5 is 1.275. So 100 degrees Celsius plus 1.275 is equal to 101.275 degrees. So the boiling point of the solution is equals to 101.275 degrees Celsius. This is the answer. And we have solved for the boiling point elevation, and now let's solve or calculate for the freezing point depression. The formula for this is delta T is equal to the molar freezing point depression constant for the solvent multiplied by mole of the solution. As I mentioned earlier, when we add salt to the water, the boiling point increases. But in freezing point depression, it will decreases. So that's the point of the boiling point and the freezing point. Take note or just remember that in boiling point, it will go as up or increases, and in freezing point, it will go down or decreases. So let's try to solve a problem. So here, 80 grams of sodium hydroxide in 500 grams of water. So the formula we're going to use is delta T is equal to the mole of the freezing point multiplied by the moles of solution. So the constant of the water is 1.86 degrees Celsius per molarity. So now we have the 80 grams of sodium hydroxide over 1 times 1 mole of sodium hydroxide. So we're gonna find the moles of the solution. First, let's solve for the molar mass of the sodium hydroxide. So the atomic weight is sodium is 23 and the oxygen is 16 and hydrogen is 1. So let's just add this and it is equal to 40. So it is 1 mole over 40 grams sodium hydroxide. Let's just cancel the units of grams, and 80 divided by 40 is equal to 2 mole of sodium hydroxide. So this is the solute, mole of solute. So to get the mole of solution, we have the mole of solute is 2 moles and our solvent is in grams, so we have to convert the 500 grams into kilograms, which is 500 divided by 1000 is equal to 0.5 kilograms. And to get the mole solution, so 2 divided by 0.5 is equals to 4 mole. So this is the mole of solution. So we have our mole of solution, which is 4. So we multiply 1.86 times 4 is equal to 7.44. degrees Celsius, and this is the freezing point. So let's find out if there is a change in temperature. So this is the formula that we're gonna use to find the change in temperature. So TF is equal to T, this is the freezing point of water. What is the freezing point of water? It is 0 degrees Celsius. And the delta T is 7.44 degrees Celsius. So 0 minus 7.44 is equal to negative 7.44 degrees Celsius. So this is the freezing point As you can see, it is negative, so when we add the sodium hydroxide to the water, which result to the negative 7.44, so the freezing point decreases or it goes down. So that's the end of our discussion about the colligative properties of a solution. Before we end it, you can try to solve this at your home, these two items about calculating the boiling point and freezing point depression. That's all. Thank you.